microphone just in case someone calls because it messes up my microphone. And here we go. All right. What do you guys notice about FTC Part 2? Now, one more time. Different books call it the fundamental theorems. This one's Part 1, that one's Part 2, this one's Part 1, that one's Part 2. The parts, some people say it's chronological, so they'd actually put this one first. I think chronologically that's how it goes. Some people say like the order should be taught. That's the Part 1. That's kind of the way that we did it. Long story short, both of these are parts of the fundamental theorem of calculus, okay? They're both kind of different parts. But what do you see that's different? First of all, do you see any antiderivatives anywhere? No. So capital F is obviously absent, right? Antiderivatives are absent, but what is present? A derivative. Ooh. So if you take a derivative of an integral, hold on, wait a minute. An integral finds the antiderivative, right? What's a derivative do? It goes back to the original. So think of it this way. The integral of velocity gets us to position. Oh, Sarah's gone. And then the derivative of position gets us right back to. So integral goes back, derivative goes forward. So it's kind of like they are inverses and they cancel out. But what do you notice? This one, literally, the derivative of the integral cancels out in a sense, and you get back to just plain old f of x. But what's different with this guy? Both of them have, what do you think A stands for in the lower bound? Any number. 0, 1, negative 10, doesn't matter. Any number. If it goes from any number to a variable, wait, this one has an x, what does this one have? So what would be an example of a u?
2x.
2x, or x squared, or 3x plus 1, or cosine of x. Okay? So if there's a u, we would end up at at the original function of u times u prime. Now, I'll try to show you why that is what it is in the examples down below. So, if we were to, this is not going to work well. If we were to try to solve this, number 5, the long way, not with the just like, oh, it cancels out, go team. All right? If we were to solve this the long way, because they didn't even give me a function. Like, I'm just trying to show you guys how this thing works. If we were to solve the integral. Question. From fundamental theorem of calculus, wouldn't it be antiderivative of b minus antiderivative of a? Yeah. Does that make sense? Yeah. If I was to integrate, solve this definite integral, think FTC, the antiderivative of b, which is x, minus antiderivative of a. Now, the derivative says, okay, now take the derivative of that. Well, kiddos, the whole point of the antiderivative is that his derivative is the integrand. So, what would be the derivative of this guy?
F of x.
Ah, little f. And what would be the derivative of the constant?
Little.
He's a constant. It's f of 2 or f of 0 or f of 1. It's a number. So, look, they end up, in a sense, canceling. No big deal. That's what the FTC says. However, what's different here? If I was to do antiderivative of b, who am I plugging in? X squared. Maybe now you can see, maybe not quite yet. Minus antiderivative of a, right? Now take the derivative. Check it. Take the derivative of this guy. Who's the derivative, or what's the derivative of the outside? Keep the inside.
Oh.
Why do I have to do a u prime?
Because
the derivative of the inside is 2x. I need the chain rule, right? And then minus, what's the derivative of the constant? 0. So do you see why FTC, part 2, this whole idea of taking a derivative, it really works the exact same way. You're taking the derivative of what would result if you were to do antiderivative of b minus antiderivative of a. The nice thing is the derivative of the antiderivative does get back to the original function in both. The problem is this one, the x got plugged in, and that was the guy who was derived. This one, x squared got plugged in. That's the guy that got derived. So I need the extra. We'll see more examples of that in just 1 second, but that is FTC part 2. Okay, we have another forever card though, right?
Yes, we do.
So who's this guy? Okay, we gotta fill him in. MVT for integration, or MVT for integrals. Have we already talked about MVT? Yes. The weird thing of this is that we're actually looking at an integral, which means we're looking at an antiderivative, not an We're looking at an integrand who is the derivative of somebody, of the antiderivative. So we don't have to say that he's continuous and differentiable because we're not looking at his derivative. He is the derivative. So if he, the integrand, is continuous, that means the original, the antiderivative, was continuous and differentiable. Kind of confusing way of putting it, but there it is. So if the integrand is continuous on the closed interval a to b, don't need the differentiable part because if he is continuous, the antiderivative is differentiable. Then there exists a number c within a to b. I think it is a closed interval. Right now in my head though, I'm kind of like balking at that closed interval. I think it's closed. Such that, all right, let me show you two different variations of this. The first one we could say, f of c is equal to the integral from a to b of f of x dx all over b minus a. That's one way of writing it. The function value will equal its average value. It's kind of like instantaneous equals average. The function value equals its average value, because this is the average value we saw yesterday. But there is another way of writing it, and the other way of writing it would be f of c times b minus a equals the integral from a to b of f of x dx. If it helps a little bit to see this, another way of writing this guy, a way that makes more sense with the MBT that you guys already know and have studied. I'll put this board down here. I could write this a little differently. I could say, you guys know that's like a little this implies error, right? I could say, does this look a little more like MBT? Yeah. Right? Because it's the instantaneous equals the average, but the dilemma is, or from what we've learned, there are other ways of writing this. The derivative of the antiderivative is the integrand, or antiderivative of b minus antiderivative of a is the integral. And so this is kind of our old-fashioned version, but this is our new way of writing it. Now the whole idea of a perfect rectangle says, hey, a base times a height is going to equal the actual. I'll try to show you the whole perfect rectangle down below on this example. Now our book says x star. Just remember it's a special x. We can call it c. X star, if our book says that. We can just say whatever. We're just going to call him c because we like c better with our theorem, with our forever card. X star, c, whatever. So, satisfies MBT for integrals. That means we have to look at this f of x as an integrand. So we can say, all right, there's going to be some place where f of c is equal to make it a little bit easier, 1 over b minus a times the integral from 0 to 3 of f of x dx. So I'm using this integral notation. I could have used this one, but this one has the c more alone, so I like that one a little bit better. We could go ahead and plug in stuff. So square root of c, plugging in c to f, is equal to 1/3 times the integral from 0 to 3 of the square root of x dx. How do I antiderive square root of x, or x to the 1/2? X to the 1/2.
X to the 1/2, that would be, you have to add 2 over 2.
Add 2 over 2, which would be x to the...
X to the 3/2, so that would be 2/3.
But I also have a...
Isn't it cube root? Oh no, wait.
It's 1/2, adding 2 over 2, which would be 3/2. Remember, multiply by the reciprocal, and I have the 1/3 also. But I still need to go from 0 to 3, right? I could combine my cool little coefficients and just say, okay, that's 2/9. I don't know about you guys. 3/2 is kind of hard on my brain. So I'm going to think of this as 2/9 x times the square root of x. It's a little bit easier on my head. Just think x to the 1 1/2, x to the 1 1/2. It's a little easier in my brain. So that'd be 2 ninths times 3 root 3 minus 0 root 0. 0 root 0 is just 0. The 3 and the 9 reduce, right? So 2 root 3 over 3. You guys agreeing? How do I solve for C?
Square root of
So then C, square root and square cancels. 2 squared is 4. Root 3 squared is 3. 3 squared is 9. So I'm getting 12 ninths. Oh wait, that can reduce, can it?
4/3.
Oh, silly. Yeah, 4/3. Whew! Is 4/3 between 0 and 3?
Yeah.
Good. Alright. So that's my C. If it wasn't, I'd say none. Now let me try to show you visually though. Let's see if I can insert a page real quick. Don't worry, I'm keeping this up. I'm trying to make it so you can see both at the same time. Let's do dual page and let's insert a page. Yeah. Okay. We know what the square root of x looks like, right guys? 0 to 3. 3 would, let's see, 1 and a 2. 3 would hit at root 3, right? Okay. If I was to find the area under this guy, it'd be that, true? Okay. What this is saying, check it. What this is saying is, if I was to do a left-bound Riemann sum and just do 1, wouldn't that be an area of 0? Right? If I was to do a right-bound Riemann sum, wouldn't that be an area of base 3 times height root 3, so 3 root 3? I know the actual area has to be in between 3 root 3. Well, actually, you know what? Looking at this picture, I know it's not equal to that upper one. Because the right approximation would, like, totally have some error, and the left one would leave out everything. But I know that the actual area has to be somewhere between 0 and 3 root 3, the rectangle. It's something in between. So by IVT, as I pick different heights to use the rectangles, I'm going to hit all of the different possible areas in between. So what MVT says is, well, okay, since you have to go from 0 to root 3 with all of your different function values, all your different f of c's, there's going to have to be a perfect f of c where the area of the rectangle will equal the actual area. So the actual area, that's the integral from 0 to 3 of square root of x dx. Intermediate value theorem says, well, if you're going to cross through all the different f of c's, you're going to have to go through the perfect one somewhere. So what we just found over here, pause, what did we just find? We found that c equals 4/3. At 4/3, there's one, let's cut this into thirds-ish. There's 4/3. At 4/3, this rectangle right here is the perfect rectangle. How much it's over equals how much it's under. So this right here is the exact same thing as the integrals area. And that's by MVT and IVT. So that's it's pretty cool. That's where it's saying perfect rectangle. There is a place. Now, how do you know it? Well, didn't we work backwards? So how would it really be helpful to like cheat and work forwards? It's not. But there is the idea that somewhere in between there's a perfect rectangle, and the perfect rectangle for this one happens when c equals. That's my perfect rectangle idea.
Okay, I'm understanding that, but on the actual problem itself, how'd you go, or why'd you do f of b minus f of 3, the square root of 3 minus 0 squared?
Oh, I rewrote it to make it easier in my brain with x to the 3 halves. And then I still had to solve my definite integral. So I had to do f of b minus f of a in order to solve this right-hand side. Does that make sense? And that's where this notation comes in with the perfect rectangle, is you could have the average value, which is the integral from a to b of f of x dx over b minus a, equals the function value, equals the height. Or you could multiply that b minus a to the other side and say base times height. There is a base times height that equals the integral. So there's a couple different ways of writing it, but it's all the same theorem. Okay, kiddos, that's the last forever card. Tyler, we're not doing U sub, not until next chapter. So let's go ahead and play with this one. I'm not telling you which forever card it is, but it might become pretty apparent. Oh, it says it in the directions. What's it having us do? Take the derivative, yeah?
Yeah.
Take the derivative. Everybody take the what do we got? It's a celebration.
It's a
You guys are
celebration.
having a party?
I want to go.
This is fun.
From Mexico.
Actually, I really want to go. Do we need chaperones? I'm not kidding about that.
Wow. What is it?
No, seriously, this is so fun.
What is it?
Oh, Chinese New Year.
Yeah, Chinese New Year.
Where?
Oh. Go Mr.
I
Richmond.
want to go. Do they need chaperones? I'm 18.
February 17th.
I mean, instead of
Yeah, that sounds pretty cool actually.
I can punch the numbers a little.
Is anybody going home for Chinese New
I
Year?
have,
You guys aren't, right? Sometimes there are a couple kids that go home. But it's a huge celebration, so I get it. Anyway, that sounds really fun. Anyway, coming back. Coming back. Kiddos, I need to take a derivative. Let's take a derivative. Do you want to take a derivative of both sides?
Oh my god. I'm serious, I'm probably gonna go. Colin, so.
Wouldn't that be cool?
Yeah,
Well,
it's
I'm
in
thinking about
Chinatown.
everybody. We all want to come with you guys. Anyway, DDX.
This will be Chinese food.
We take a derivative of one side, we take a derivative of the other side. Yeah? Take a derivative of one side, take a derivative of the other side. So the derivative of, well, we know that's just f prime, capital F prime, whatever, it's the derivative, it's notation. How do I do this one?
Wait, the plus and T's.
Yeah, it's the same.
So what should I write?
What?
It's actually right, because here's why. If I was to antiderive, wouldn't the x get plugged into his antiderivative? And wouldn't the pi over 4 get plugged in? It starts in terms of t, but it's going to become in terms of x.
So you can just already have it in terms of
So I can exactly. Dun 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 dun. What?
Oh,
Wait, what?
No.
No, I'm right, and here's
I
why.
can't do that.
Here's why.
I don't get it.
Your bounds, look at your favorite card, are a, doesn't matter, it's constant, to x.
I'm enjoying my
The
life.
derivative from a to x of an integral is itself with x plugged in.
X plugged in.
Yeah. Hold on, come back.
Oh, yeah.
I kind of understood this.
You guys would have gotten mad at me if I showed you earlier, but we're going to change our forever card.
Oh, good thing I'm not with you.
Because the x comes in later, technically, you will always see,
What do you, David?
oh no,
A different variable?
you will always see a different variable inside. But you still end with the x.
Oh.
Because the x gets plugged in,
So basically, you just did an example that you didn't teach us.
basically. I waited until I taught it, until I could.
I mean, semi-rude, but it's okay.
So the x comes in with the bounds. The x comes in with the bounds. But guys, check it. I had something in here, cosine 2t. The x came in, cosine 2x, when I took a derivative. No big deal.
Wait,
No big deal.
Wait, just really quick question.
Yeah.
Does the quiz start at number 29, the definition of the antiderivative?
Were there integration rules before that?
No, it's just little detail.
Okay, then yeah. 29. The bonus might come from somewhere earlier, but besides that. What are you looking for?
Let me see if they put-
Oh, top shelf of the cabinet right below. Manila folder. Oh, sorry, this cabinet. Yeah, because tomorrow's the 31st, because the Chick-fil-A fundraiser. Go team! Yeah.
So why is this helpful? Like, what's like the application of this?
I thought you would have stopped asking some like algebra.
I don't know. I'm just kind of confuzzled.
Let me just put it in context of the AP exam. Sound good? They're going to give you an expression at the very beginning of a big old FRQ. And it's going to be the foundation for the entire FRQ. And they're going to give you an expression that equals an integration. We call it an accumulation function, where we know where the starting point is, but we don't know the ending point. The ending point can be many different things. You can think of, we're trying to think about displacements without really knowing exactly or even caring exactly about the ending point and wanting to consider all the different ending points. So we're dealing with an accumulation function, and this is just one part of analyzing that accumulation function. Because if this is the main guy, the main quantity that we're trying to think about with all those different like displacements, then it might be helpful to look at his derivative for like whether or when that displacement is increasing or decreasing. Does that make sense? But in order to do that, we have to know this formula. Because sometimes there might be, like in this one, it says check the result by first integrating and then differentiating. Now, here's a bit of a struggle. You guys don't know how to integrate this guy quite yet. And on the AP, they'll give you a guy that maybe you can't integrate. So the struggle, Sean, is what if we're given a function for rate that we can't integrate by hand? Can we still work with that function? And the answer is yes.
Couldn't you just double angle that?
Double angle it? Yeah, but then cosine squared minus sine squared is even worse. Good idea. Long story short, let me anti-derive this guy. Let me anti-derive this guy for you. Tyler, you can play with U sub a little bit if you want. I'm not going to show you all the what, why, wherefore, but you guys can check me and see if I'm right. The antiderivative of this is going to be 1/2 sine of 2t. Check it. Derivative of sine of 2t is cosine 2t times u prime times 2. Oh, whew, the 1/2 cancels out the 2. You don't have to do this by yourself yet, but it's a thing. And we have from pi over 4 to x, taking the derivative. When we do the derivative of that guy, it's going to be 1/2 cosine of, well, hold on, don't we have to plug in first? So the derivative of 1/2 sine of, oh, see, there comes in that x. That's why it's a dx. Minus 1/2 sine of 2 times pi over 4. I'm going to be super lazy and leave it like that because I'm about to take his derivative. And what's the derivative of any big old nasty constant?
0.
Aha! He's gone. And the derivative of this guy will be 1/2 times cosine 2x times 2. Or we write doing it the fast way. Yes! So let's do it the fast way. Now, remember, this jump you're not expected to have to make until we take this test and get into a new chapter. New part of the chapter. That's an integration technique we haven't learned yet. But Sean, one more time, they might put something in there that you can't integrate, so there'd be no way to take the derivative and think about increasing, decreasing, unless you had to do. What if they gave you something like, ooh, neat guys. Pause. Why am I putting f of u times u prime? That's what I need to use. Because I have a u. Now, do I have an a to u? Yeah. Okay, so how do I apply this? Who is your f of x? Who is your f of t? That guy, right? So then think about it. This is just an a. It just makes it legal. It makes no difference on the answer because eventually his derivative of this part plugged in is 0. It doesn't even matter. So what does matter is this x squared. So guys, I need to get this x squared into the t spot. You see it? I need to get the u, the x squared, into the t spot. So my final answer would be e to the
Whoa.
2 u times u prime. U was x squared, u prime is 2x. So then we go to plug in the x squared to the t spot, and then multiply it by the u prime. So final answer, 2x e to the 2x squared. Does that make sense? Now pause. What are we doing the next one? He's not written right.
Can we, well, you can
Well, the
flip it
negative
and
is
turn it
not
negative, right?
Isn't there a property where we can flip the bounds? So can't we say this is dx of negative? We have to make it legal. We have to make it legal. We have to make it from a to x or a to u. But now that we flip the bounds, can we just use our theorem? FTC says ultimately plug in the x, a to x. So my final answer is negative x squared. The negative stays, the x gets plugged in. that kind of make sense? That's FTC. Do you have anything else for MVT? No? Got it. Even answers? Onward. Let's do this, because you guys are supposed to be finishing this up tonight, yeah? All right. Why don't I have you guys, because I did want to start the review. Let's see if we have these homework solutions ready to go. I have 4.1 ready. I'm not sure if I got all the way to 4.4. Have we already checked 4.3? We did, right? Oh, I do have 4.4 ready. All the way? You guys only had 3 even? 1, 2. I think I wanted you guys to be able to check pretty good, huh?
Yeah.
Okay, if you guys want, why don't you take a picture of these evens and have them ready to check tonight once you do them. Come in tomorrow with questions knowing all the answers. Does that sound good? Let me try to full screen this real quick to make it a little bit prettier. There you go. Go ahead and take a picture of it real quick. Because there's only 3 evens. And that way when you try homework you can check the evens. Some of you haven't gotten to like 116, maybe even 50. Oh, 50. Oh no, 50 was MVT. Yeah, I see it. 50 was MVT. Alright, then let's end class. We have, what, almost 10 minutes? Get out those practice tests. Get out those practice tests. Let's play a little bit tonight. We'll work on homework. You'll finish, you'll check. Come back tomorrow with questions. Sound good? Okay. You already have the evens. You can already check them. But let's grab out that practice test and let's play. Because tomorrow we're going to go over questions that you have on the practice test and or homework. We're going to have a work day for the majority of it. So if you're on a practice test, if some of you guys want to update your forever cards first, that's also what I would say a very valid use of your time. You can update your forever cards, but I would say let's play with that practice test and see if you get stuck yet, and I can help you power through a little bit further. Sound good?
Stuck.
Just sit out of the cup.
What?
Sit out of the cup.
I'm such a wuss when it comes to cold liquids on my teeth. Oh. It stirs from 0 period. Yeah, 0 period in the morning.
I'm gonna tie it.
I do have basketball games today, so just giving you guys a heads up. That's starting at 3:30. I will be a bit indisposed.
No, please, David. I'm gonna give you a shirt. My name is David.
I worked hard in this class. Not really. I want at least a 0 plus.
Not 0 minus.
Wait. Oh.
1, 2, 3, 4, 5. Nice.
Feel free to talk things through, kiddos. You don't have to be silent. If you're working on stuff, it's also very, very good. So.
Where's speed? What number 1? Where? 34. Total displacement versus. What's that? This one? Increasing versus
All right, Sarah and Sam, we're leaving you. See you tomorrow, hopefully.